everyone, it's Justin again. Today, we're going to look at another application that uses rational equations, distance, rate, and time problems. By the end of this lesson, you should be able to solve distance, rate, time problems that use rational equations. First, we'll discuss how distance, rate, and time are related. Next, we'll organize steps to help us solve this type of problem. And finally, we'll complete two examples. First, let's talk about how distance, rate, and time are related. We have the formula, rate times time equals distance, or shorten this, r times t equals d. For example, if you travel at 60 kilometers per hour, and you do this for 2 hours, you'll travel 120 kilometers. If we think back to when we solved work rate problems in our previous lesson, we used the reciprocal so that our unknown was in the denominator. It'll be the same here. In the problems in this lesson, we'll be trying to find rates. So we want r to be in the denominator. How would we get r in the denominator? Well, we divide by it. Now we have that t equals d over r. This equation is super important, so add it to your notes so you have it ready. Now let's look at the steps we can use to solve distance, rate, time problems. There are 4 steps, and the first says to fill in the table. The table looks like this. You put the rate for the first event here, and the distance for the first event here. The rate for the second event goes here, and of course, the distance for the second event goes there. Then we move on to step 2. This says to set up an equation. We'll see 2 types of equations, and they'll both come from the formula we talked about earlier in the lesson. Time equals distance over rate. Since we have 2 events, we'll use the formula twice. We can set it up for event 1 using d1 and r1. We also have the same setup for event 2 using d2 and r2. We may be told in the problem that times for both events equal each other, and if that's the case, then we set these equal to each other. This is where our first formula comes from, and there will be one other option that we can use in our problems. If you see that the 2 times from the events add together to equal a total time, we'll use this, but we can replace t1 with d1 over r1 and t2 with d2 over r2. This is where our second equation comes from. These will be our 2 options for equations when we start solving scenarios. Our third step is to solve whatever equation we have. This will involve using the cross product or the LCM of the denominators, just like we learned in the previous lessons. And our fourth step is to go back and make sure that we answer our original question. We're going to use these steps to solve 2 examples in this lesson. So take a moment to pause the video if you need to finish taking notes on any of this. All right, moving on to our first example. It says that with no wind, Jaime rides his bike at a rate of 14 miles per hour. It takes him the same amount of time to travel 8 miles with the wind as it does to travel 6 miles against the wind. How fast is the wind blowing? You may feel completely lost on how to even begin this type of problem, but that's what we have our steps for. The first step is to fill in the table. We can think of our 2 events as riding with the wind and against the wind. When riding with the wind, he's riding at a rate of 14 miles per hour plus the wind helping him. That's represented by 14 plus x, with x defined as the speed of the wind. When he's riding against the wind, he's riding at a rate of 14 miles per hour minus the wind, since it's a force working against him and slowing him down. Then we fill in the distance column. The distance he traveled with the wind is 8 miles, and the distance he traveled against the wind is 6 miles. Let's move on to step number 2, setting up an equation. We only have 2 options for equations in this lesson. we'd use the first equation if the times for each event equaled each other. And we'd use the second equation if the times for each event add to equal a total time. So let's look back at the scenario and see what we were told about the times. We were told that both events took the same amount of time, which means they equaled each other. So we'll use the first equation. We can substitute all of our values from the table into this equation now. Our first fraction represents the distance and rate with the wind, and our second fraction represents the distance and rate against the wind. Now that we have our equation set up, let's move on to step 3, which says to solve. So, how can we solve this? Yes, we can use the cross product. Why don't you pause the video and take it from here? Did you multiply opposite numerators and denominators? Did you distribute to get rid of parentheses? Finish solving by isolating x on one side and then dividing. Since 2 is not extraneous, this is our answer for x. Step 3 is complete. Finally, step 4 says to answer the original question. This is similar to our previous lesson where I said over and over to make sure you can interpret what your answer means. Remember that x represented the speed of the wind. So we can say that the wind is traveling at a rate of 2 miles per hour. Great job. We have one more example, but if you need a little more time with this one, go ahead and pause the video. Here's our second and final example. Gigi drove 120 miles in a storm and another 300 miles after the storm stopped. When it wasn't storming, she drove 20 miles per hour faster than when it was storming. Her total drive time was 10 hours. How fast was she driving when it wasn't storming? Let's refer to our steps to help us solve this. The first step is to fill in the table. We can think of our two events as storming and not storming. When it is storming, Gigi is driving at a rate that we don't know. So we'll call this x and define x as her driving rate when it's storming. When it's not storming, she could travel at a rate that is 20 miles per hour faster. Then we fill in the distance column. The distance she traveled in the storm was 120 miles, and the distance she traveled when it wasn't storming was 300 miles. Let's move on to step number 2, setting up an equation. Let's look at our two options for equations again. We'd use the first equation if the times for each event equaled each other, and we'd use the second equation if the times from each event add to equal a total time. So look back at the scenario and see what we were told about the times. Pause here and see if you can figure out which equation is best and why. We were told that both events add to equal a total time of 10 hours. So we'll use the second equation. We can substitute all of our values from the table into this equation. Our first fraction represents our distance and rate when it's storming, and our second fraction represents the distance and rate when it isn't storming. Plus, that 10 represents the total drive time. Now that we have our equation set up, let's move on to step 3, which says to solve. So, how can we solve this? We would need to use the LCM method. So let's look at the denominators. The first denominator is x. The second denominator is x plus 20. And the third denominator is technically 1 if we wanted to write it. So, what's the least common multiple of all these? It's x times x plus 20. All right, you can take it from here. You've got this. Now that we've multiplied each term by that LCM, just simplify the equation and solve it from here. Let's see if your work matches mine. Canceling the x's from the first numerator and denominator and the x plus 20s from the second numerator and denominator gets us here. There wasn't really anything to cancel on the right side of the equation because the denominator was just 1. Then, distribute to get rid of the parentheses. Combine like terms on the left side of the equation. Then move everything to the same side as the x squared to keep x squared positive. Divide all terms by 10. Reorganize the equation if you prefer to see it this way. Factoring this time is going to be a little tough. What multiplies to equal negative 240 and adds to equal negative 22? It may help here to make a list of factors of 240. Do you see it now? Can you make one of the numbers negative? It's 8 and negative 30. Those multiply to be negative 240 and add to be negative 22. Now that we have this factored, we set each factor equal to 0 to get our solutions. While neither of these is extraneous, one of them won't make sense in this scenario. This is a reason why step 4 is so important. So, what does x represent? We defined x as her driving rate when it's storming. She either went 30 miles per hour when it was storming, or negative 8 miles per hour when it was storming. A negative number would not make sense here. So we say she went 30 miles per hour when it was storming. Now, do we answer the question that was asked of us? Actually, no. The question asked how fast was she driving when it wasn't storming. So we add 20 to this to find her speed when it wasn't storming. We get that Gigi was driving at a speed of 50 miles per hour when it wasn't storming. Now you can solve distance, rate, time problems. Remember to follow the 4 steps. Fill in the table. Pick the equation setup to use out of these 2 options. Solve it using either the cross product or the LCM method from previous lessons, and be sure to answer the original question. See you next time. Hey.